Okay, we're now on page 3 of the AP Concentrated on Concentration. 13 is going to demonstrate where we stopped on number 12, showing that the relationship between milligrams and liters of arsenic will generate parts per million as the same if we were to have a mass over mass of the sample with the same units. So far I've been leaving everything in the ratios when we've been calculating it. I will spread it out into 2 pieces this time. Our goal is to find grams over grams. So that's, you guys know this is solute, total solution. We don't have to add the grams of solute and solvent for solution because when you do, it becomes obsolete. When I break this down for you, I will show you exactly how that works. So what I'm going to do for the top is I'm going to just convert milligrams into kilogram. Milligrams into grams. 0.750 milligrams for every 1,000 milligrams. You got 1 gram. Remember, when we do unit conversions, we're just multiplying by a factor that is equal to 1. That's not changing the value of our initial value, our given. We're just changing the units. So this will give us a 0.00075 grams of arsenic. And we're a short moment away from being responsible for the names and symbols. It's our next step in nomenclature when we come back. So arsenic is AS. Blah, blah, blah. Where were we? Oh, yeah. Getting a liter of grams, liter of a sample of water into grams. So I'm going to now work on taking just 1 liter of water. And for every 1 liter, there are 1,000 milliliters. And then we know for every milliliter of water, it weighs about 1 gram. So now we end up with 1,000 grams of water. And we can go ahead and call this the total solution, even though it's just the solvent. And I'm going to go over here real quick off to the right and show you why. If we were to take 0.000750 grams of arsenic, and then we were to add that value to our grams of water, we'll find that our total solution becomes 1,000.000750 grams. And what happens is only in some very, very, very strange circumstances where you have something like, what do we got going on here? Like, oops, that's even a 0. We end up with so many, oh, hold on, I have to pause this because my phone is ringing. Sorry, my 3 boys are at the store and wanted to know if they could get a treat. Okay, so here we see that we only have 3 sig figs in the top, and we now have generated this many in the bottom. And when you do the math, you find out you can't count this many sig figs anyways, and you end up not being able to report them in your answer. You can go ahead and try that and see what kind of answer you get, and you'll see that, we could do it. What the heck? Let's do it. So, a little bit more light. 0.000750 divided by 1,000 0.00750. And right now, where you're going to get good at your calculator, right now we're in flow. I'm going to put this into scientific notation. And you see that we can only report 3 sig figs, which would give us 7.50 times 10 to the negative 7, which would be the same as 0.750 ppms. We're never going to, so it doesn't matter if we add this or not, because let's just not do it now. Let's just say 0.000750 divided by, and now we're going to exclude this and just consider our grams of solution, divided by 1,000, and you end up with the exact same number. You'd have to know to add a 0 here when you're in scientific notation. You can never trust your calculator. You have to know how to just add a 0 and make that significant. So here we've taken the solute divided by the solvent, since we're dealing with such extreme numbers, and we get 7.5 times 10 to the negative 7. Since we have to report this in parts per million, I'm going to times that by 1,000,000 times 1 million. Or you could put 10 to the 6. It's the same dealio. Did I go one too many over? 1, 2, 3, 4, 5, 6. And we get 0.750 times 10 to the 1. You're going to have to learn that this is the same thing as 0.750. Put that back into flow. I love this calculator for chemistry, so you'll have to remember to report the 0. We have 3 sig figs here, 3 there. We need to report 3, so you need to add that 0. It's significant and it's been measured, and then you'd put ppm. Let's show the other units. Another way of showing parts per million is you don't the units without converting to grams to grams. If you just leave it in milligrams per liter, this is 1,000th of a gram times 8,000 milligrams in essence. So we end up with 50 milligrams per 1 liter of water. Gives you the same dang thing. So you have to know that when you have a difference of 1,000 units or a million units, it's the same as writing parts per million if they were the same units like we did. Okay, we're going to focus on molarity for a while. It's the most common. If you say the word molar, it means molarity. If you see a capital M, I try to make that very clear. Or if you see concentration brackets, that all is the same thing as molarity. And our units for molarity, anyone? Yeah. Molarity, mole per liter. Moles of solute per liter of solution. So, what is a molarity? So we're solving for big M. What's big M? Of a solution made from 2.4 moles of sodium chloride. And water. It says this is saying in the 2 liters there's 2.4 moles of sodium chloride, so it's quite simply 2.4 moles divided by 2.0 liters. Easy does it. 2.4 divided by 2, 1.2 and molar NaCl. Easy does it. Okay, what is a molarity of 500 milliliters of solution made from 0.7 moles of lithium chloride in water? So, still just working with molarity. Super easy ones here. This is definitely Gen Chem level. 0.70 moles of lithium chloride dissolved into 500 liters or 500 milliliters. We don't want to put 500 milliliters because we need moles over liter. I will show you how to write this out, but you're going to do this so often, you'll just know to scoop the decimal point over 3 places. For every 1,000 milliliters, we have a liter. And essentially, we end up with 0.500 liters. 500 milliliters is half a liter. 1,000 milliliters is a liter. Reasonable enough. And this is of the whole solution. Forgive me while I use my calculator. 0.7 divided by 0.5. 1.4 molar. Lithium chloride. My dog is being fussy. Oh, hold on. And we are recording again. Okay. This is more along things you'll have to do in the middle of an advanced problem. And now we're trying to quantify how many grams of sodium chloride are in a certain amount of a certain concentration. Let's go real quick back to this. How many grams of sodium chloride can you find in 2.2 liters of a 0.3 molar solution? Let's go ahead and get the concepts here down. Okay, so we have a solution that's 0.300 liters, or molar. Is that molar? Yes. So that means that anytime we have 1 liter of solution, we'll have 0.3 moles of the solute. So if we were to pour this whole thing out, we would have 0.3 moles. If we were to pour half of it out, we'd have 0.15 moles, etc. So what we're doing is giving you a certain amount of this. I've given you 2.2 liters of this. So we would need to find out how many moles are in 2.2 liters. Because remember, this is sodium chloride floating in here. And if I pour out 2.2 liters of it, I'll have a certain amount of moles. And from there, we can easily use the periodic table to figure out how much that would weigh. And super applicable. We need to be able to move from something we can weigh out in the lab. Ah, my dog. Let me let her out. My tortoise is making noise. Can I pause it? Are you kidding me? So, I think I just have